presentation. We've got quite a number of participants that are already logged in. It's a little bit less than the registration. We had a lot of registration for this, but I think it might be time. It's already 5 or 6 minutes after 5, so it's time that we should make a commencement. Just the way it works, you've probably seen these webinars before. My colleague Martin Muxworthy from Nexans Olex will do the first part of the presentation, and then I'll follow on from that. At the end of the presentation, Voltimum have got a very quick survey that they would encourage everybody to please have a look at the survey. There's just only a few questions involved in that, and they value your opinions because this information is then used in future surveys to try and make things better. As far as questions go, if you have a question during the course of either of the presentations, please use the chat window, which I think you should be seeing at the bottom of your screens. Type in your question and Martin and I will have a look at the question. We'll acknowledge it. If it turns out to be a quick response, we'll answer it on the spot. If it's something that requires a slightly longer response, we'll just let you know that we'll handle that question towards the end of the presentation, only because it's going to be a longer response. So without further ado, I'd like to introduce Martin Muxworthy from Nexans Olex, who's going to talk about the evolution of Australian fire safety standards and their application to electric cables. Over to you, Martin.
Yeah, thanks, Ian. Thanks for the intro, and we should get straight into it. My name's Martin, and I work for Nexans Olex in Melbourne, and I'm going to talk about a bit about standards and particularly fire safety standards as appropriate for electric cables. The word fire-rated cable gets used quite a bit in the industry. It's reasonably well known, but it's still worth recapping on the essential characteristics of what a fire-rated cable actually is. And then what I'll do is I'll look at the standards that are applicable to confirm the characteristics of fire-rated cables. One thing I should do is just to make sure if someone from the audience can just let me know that they can hear me okay, and we'll continue to proceed. Then what I'll do is have a look at the differences between, if I can just write something in the chat window, that'll be fine. Then we'll look at the differences between Australian and other international standards for fire testing of cables. A bit of a look at how fire-rated cables are constructed, and then a look at how the standards are aligned with the building industry in Australia. But first of all, fire-rated cables, what are they and what are they all about? There's 4 key elements of a fire-rated cable. The first one being that they're flame retardant and do not propagate fire. And I'll expand on each of these elements a little bit further, but this is just a quick summary of the 4 key elements of a fire-rated cable. The next one is that they don't produce a lot of smoke, and I guess that's fairly obvious. That assists in getting people out of buildings if there is a fire. Zero halogen. This may not be quite so obvious, but halogens are a specific group of elements that create a lot of toxic fumes and corrosive byproducts when they're burnt. So halogens are something that we try to eliminate from fire-rated cables. And the last one is a very important one, and that is that fire-rated cables maintain circuit integrity. So that means it keeps electrical equipment going during a fire, and we'll talk about that a bit later. So flame retardant cables, yes, as I said, do not propagate fire. They're self-extinguishing, so even if a fire has started elsewhere and the cable's in its path, the whole idea of flame retardant cables is that they do not spread fire to other areas. Typically they're used in buildings, anywhere where there's a lot of people, plants, and so on, as I've indicated there. I guess the other aspect is that not only do they stop fire spreading from one area to another, they also avoid adding fuel to a fire, so it stops the fire growing in that regard. And what we do to try and make a cable flame retardant is we need to incorporate flame retardant materials typically in the cable sheath, and it's a tricky combination of where you put these flame retardant materials. In order to check, say, a material and its ability to retard fire or its flame retardant properties, one of the basic tests that are done is the oxygen index test, and it just checks the amount of oxygen in air required to sustain combustion. And as we know, air contains 21% oxygen, so any material that has an oxygen index more than 21 means it's going to be difficult to burn in normal air environment. So it gives us an indication of how difficult a material is to burn. The next series of tests that I'm going to describe talk about flame propagation of the cable itself, not materials, but the cable itself. The first one is a fairly simple single cable test. All cables made to AS5000, for example, need to pass that test. The test method is detailed in AS1660 Part 5, Part 6, and that's linked to the IEC standards, for instance, IEC 60332 Part 1. And those standards date back a long way. I mean, that standard was first published in 1970. So, as you can see, the standard is quite well established. And it's something you'll notice with a lot of these tests. A lot of development's gone into, a lot of research has gone into developing the standards, and the repeatability of the tests is quite good these days. The next part of, or the next test that we're going to look at is where cables are bunched together rather than a single cable. Cables being bunched together. And in this particular test, as detailed in AS1660 Part 5, Part 1, there's a defined volume of combustible material which you have to have, and there's different categories related to this particular test depending on the volume of combustible material. And as you could deduce, the more combustible material, the more fuel it adds to a fire, and the more difficult it is to stop flame propagating. So when you have lots of cables together on cable trays, it's a lot harder, and so therefore to pass this particular test is more difficult than that first single cable test that I just mentioned. So you'd be typically looking at cables with, say, materials of higher oxygen index, for example. Moving on from flame propagation, that second element which is important in fire-rated cables is that of the smoke that cables produce when they burn. Fire-rated cables, we typically look for zero halogen content and low smoke materials. So the materials will not contain any of the PVC, for example, has got chlorine in it. It won't contain chlorine or fluorine or any of those halogens. And the problem with the halogens is any material that's got a halogen in it, when it burns, it tends to produce lots of smoke and also corrosive gases, which you want to avoid, so that you prevent damage to sensitive electronics and so on. And I guess the problems with smoke inhalation are fairly obvious. Not only is it difficult for people to breathe, if there are toxic fumes around, but it also makes it difficult to see, exit paths from buildings and so on. So that's the basis of why we're looking for low smoke and zero halogen cables. To check the amount of smoke that cables give off, or in this particular case, we are specifically talking about cable tests. Another series of standards, 1660 Part 5, Part 2, for example, has a has a smoke density test, and it's an interesting test in that a large 3 by 3 by 3 meter smoke chamber is what's used. Inside the chamber there's a sample of cable. A small tray of alcoholic mixture is used as a flame source, and essentially, as you'll see from a little image there, a light source is shined on one side of the chamber, and a light detector on the other side checks how much light it can receive from the light source. Low smoke cables typically, you need to have at least 50 to 70% of light transmitted through that chamber when the sample is burnt. Again, a lot of these standards originate from quite a while back, 1660 Part 5, Part 2, 1992, and I think what I'm also demonstrating is that our Australian standards evolved predominantly from the IEC standards, and in this particular case IEC 61034, and they date back to the early 1990s, for example. So we've talked about how we measure the smoke that's given off cables. There's some other tests that determine the acidity of the smoke, and believe it or not, it sounds a little strange, but it is possible to detect and measure how much acidity is given off a cable, and this involves burning a small sample again, and this is inside an enclosed, what they call a tube furnace. And what really happens is there's a number of ways it can be done, but one example is air is pushed down the enclosed space, and what you do is you drive the smoke and the air through a number of bottles of water, and so what happens is any particles and residue in that smoke gets collected in the water, and from there you can measure the acidity content, and in the next slide you'll see that not only can you measure the halogen acid content, you can also measure things like the pH of the water, so this will tell you the degree of acidity, and you can also measure the conductivity of the water. Same test setup is used, and these are described by another group of AS 1660 Part 5 standards. This particular one is Part 4, the previous one was Part 3. So again, these are all based on the IEC standards. These are derived from IEC 754, originally published back in 1991. So what we're finding the Australian standards are doing these days is, in a lot of cases, adopting the entire content of the IEC standards. Some of them align, like I've got indicated here. Some of them are adopting the entire content. In other words, it's a word-for-word adoption of the IEC standard. The final key element of fire-rated cables is circuit integrity. So here we're talking about trying to make sure that cables keep working during a fire. Other terms that are commonly used to describe a cable which has got circuit integrity is fire resistant. Fire resistant cables, I guess it's a little bit might be not understood that well, but you can get fire resistant cables that are not fire rated. All we really mean by that is a fire resistant cable would just have the circuit integrity element, but it may not necessarily have, say, the low smoke element. Where are circuit integrity cables used, or fire rated cables used? Buildings, plants, enclosed infrastructure, and I've mentioned a few other areas there. Anywhere where the function of the circuit is essential, and critical for to continue operating during a fire, and I guess lighting for exit paths, things like that. Fire alarm and security cable, fire safety in buildings, in the case of say lift mains and things like that, are where they're commonly used. Water pumps, which should be fairly fairly obvious that water pumps need to be able to operate in the case of a fire. In talking about circuit integrity cables and standards, there are two essential or fundamental types of standards used to describe and test the circuit integrity performance of cables. One is what we call a ribbon burner test, and these are the IEC 60331 series, the 1660 Australian Standard Part 5, and there's also another, and there's many more standards like these, but these are the principal ones that are used around the world. As opposed to the furnace standard test, the furnace standard test is described in the AS3013. And we'll look at each of those in a bit more detail in a moment, and hopefully the differences will become fairly obvious. In the case of the ribbon burner standards, covered by 1660 Part 5, and as I mentioned, this one actually adopts the entire content of the IEC 60331. We go back to quite some time when 60331 was first developed, which is first published in 1970. So again, an indication that these standards have gone through a fairly rigorous period of development and have established themselves in the industry. The next few slides discuss how the test is actually conducted. And there's a number of elements to this ribbon burner test as I've described it. You can have fire alarm, which is as depicted on the image at the left. Fire alarm consists of the ribbon burner, as you can see there, and then the cable sample is supported, clamped near its ends, and then there are two rings that are there that are within the fire or the flame region, and the whole idea is to obviously ensure that the cable continues to operate, so there's no short circuit between conductors, and there's also no short circuit between the conductor and these metal rings. So you can have things like fire alone, and typically the fire alone test is done at 750 degrees, or you can have fire and mechanical shock. And what this little picture here is meant to describe is the cable itself is clamped to a metallic ladder type tray. The burner is positioned to obviously burn the cable, and then an iron bar is repeatedly struck against the tray to introduce a shock type mechanical shock type system. And it's just really to, I guess, as a more severe or onerous way of proving that a cable is going to survive in its more practical application. Fire and mechanical shock is normally done at 830 degrees, and it's interesting reading through the standards how you actually validate the temperature of these tests. Validation is done actually prior to applying a cable into the test setup. Thermocouples are used to ensure that the amount of gas and airflow rates, for example, that come out of the burner are adjusted to achieve the temperatures required. So that's validated before the test, and then the cable's put into position to actually proceed to do the test. The other ribbon burner test that I mentioned was a British standard, 6387. Similar sort of test arrangement. It introduces some different category type classifications, different temperatures, 650, 750, 950 degrees. That's for fire alone. I guess the difference with this particular standard is that there's an additional water sprinkler test that you can do. And I think the next slide talks about, no, sorry. In preparing this presentation, I've also written an article which will be published I'll voltage them in the next day or so, and this gives a bit more elaborate detail on the intricacies of BS6387. Suffice to say that things like adding a water sprinkler to the test is to simulate, say, water sprinklers going off inside a building or in a basement or wherever the cable might be. That they just try to simulate something that happens in real life. And then this standard also has the fire with shock at the same 3 temperatures, and you might see logs of fire-rated cables, and they might say they comply with BS6387 category CWZ. So that just means that they've been tested to 950 degrees for fire alone, fire at 650 with sprinkler, and then fire with shock at 950 degrees, for example. The next part of this presentation is about the furnace standard test of 3013, AS3013. Again, this has been around a long time, but it goes away from those IEC standards which I've been talking about. It's fundamentally quite different. The test is done in a furnace as opposed to an open ribbon type burner, and we'll get to see the furnace in a minute. This standard is applicable to all wiring system elements, and this is an interesting one. Things like cables, busways, supports, cable trays, for example, fixings, saddles and tyres can all be tested in this standard. And the cable itself, the current version of the standard requires that the cable is tested on a cable tray. Again, that's to simulate, pretty obvious, that the way that a cable would be installed in practice, and I guess it's taken for some some generations of development of this standard to come to that point, and that's what all cables tested as standard. They must be mounted on a specified cable tray. There's also an additional water spray test, like I'd mentioned with the British standard, to simulate fire extinguishing methods. And the other thing is, I talked about the validation of the IEC 60331 standard. In this particular furnace standard test, it is done according to a defined time and temperature curve, and this is specified in AS 1530 Part 4. I know there's lots of standards that I've been mentioning, but hopefully it all makes sense. Just to run down a quick summary of how 3013 defines this wiring system classification, and people that have used fire-rated cables would be familiar with this wiring system classification. I use the example of WS52W, and that's what most fire-rated cables comply with. That means 120 minutes or 2 hours fire test, an impact and cutting test of rating 2, which is, I guess, what is deemed to be most common for say, polymer cables, plastic or mix or PE insulated cables, for example. And then the W means it's a supplementary water test has been applied to the cable. Just some pictures of the fire test itself. The photo on the far left shows how the cables are mounted on a cable tray prior to doing the test. And hopefully you can see and get a feeling for the severity of this particular test. This is a photo of the furnace lid being removed so that it can be taken over to do the water spray test. As you can see, the cable tray and the cables are glowing red hot, and that gives you some indication of the amount of heat that's in there. It's in an enclosed, this furnace is an enclosed, it's several meters long and probably a meter deep, for example. So it's quite a significant size furnace, and what you're seeing here is the lid of the furnace being lowered into an area where it will be sprayed by a water spray, and it's got to survive a water spray for about 60 minutes, I think it is. I mentioned the time temperature curve. This is what's defined in AS 15 30 Part 4. And by no coincidence, it's the same time temperature curve that is used and referenced in the building standards to apply to building materials. It's what's categorized by a cellulose fire. So it's a time and temperature curve that would be typical of a fire, started from timber and similar type of building materials containing cellulose. So as you can see, in the 2-hour time period governed by AS 3013, for example, the temperature achieved in the furnace is over 1,000 degrees. So there's a fairly obvious conclusions that can be derived from this particular curve, and that is that copper conductors, for example, is the only type of material or metal commonly available in the cable industry that can survive this test, because it's got a melting point about 1,083. I've just been asked if anyone has any questions. I mean, I've been going sort of fairly continuously. Feel free to ask questions or pause me if you need to, if you want me to elaborate on something. No problems with that. Just to keep going on the final part of 3013, there's a mechanical impact and cutting test, and these little images give you an idea of how the impact and cut test work. Impact is a set of weights. It's got what would you call it, a bar positioned in the center of them, and the weights are simply dropped on the cable a number of times. And of course, the cable's got to continue to carry current, and it's not allowed to short circuit to either the platform or the cutting object, or the impact object, I should say. In the case of the cutting test, the cutting tool is a small wedge that's applied with a compression testing device, and again, similarly, the force is monitored and controlled to apply a certain force depending on the cable size and the category that you wish to meet. So that's how these two, the mechanical side of the 3013 test is determined. I've got one slide here that talks about how fire-rated cables are constructed, and I summarise this fairly into a fairly concise single slide, because when you look at it, there's literally only three types of ways in which fire-rated cables or cables with circuit integrity have been developed over the past 100 years. And some people might be surprised to learn that MIMS cable, which is a mineral insulated and metal sheet cable, was actually invented prior to the 1900s. And I think maybe the inventors didn't quite realise what they invented at the time. It wasn't until much later on in the mid-1900s that people learnt of its value in fire or circuit integrity type applications. Magnesium oxide insulation makes it a very high temperature rating, and of course the copper conductor and the copper sheath enable to also operate extremely high temperatures. The next, I guess, development or innovation in fire-rated cables came in the 1970s, when I think people looked at other ways of alternatives from the MIMS cable, and it involved the use of mica tape. Mica and glass tapes wrapped around the conductor served as a simple means of ensuring that the conductor would remain insulated in a fire condition even after all of the say the PE or sheathing materials burnt off, because at the time there weren't any special materials that would resist fire in the way that's required during a circuit integrity test. Not until a new group of materials came along, which are called ceramifiable, and they were developed around 2004 jointly between OLEX and the CSIRO. Very special proprietary insulation material, and it basically turns to a hard ceramic-like material during a fire. So it's quite an ingenious and special material, and as you can see, as opposed to the mica tape cable, this particular cable only has 2 layers. Sheathing material might be very similar on each. They'd be an HFS type material, but the ceramifiable design doesn't require the mica tape, so there are some OH&S issues with the use of mica and stripping it. So that does away with that material, but I mean, it's not to say that mica tape is still not in very widespread use today. It is. It's very popular and certainly it's placed in the use today. The last slide looks at briefly at the Australian Building Code Board, the National Construction Code that details fire safety systems in buildings, and in reading some of the elements of the National Construction Code, you see that it talks about fire resistance of walls and floors and all sorts of common building components, and it develops a sort of a similar category or fire resistance level that I've been describing in AS 3013, and it describes like a 3-part, in this format, X, X, Y, Y, Z, Z, and they relate to time in minutes to failure. XX, for example, relates to the structural adequacy of the load-bearing element. YY relates to the integrity of the building material. So, in the case of maintaining a barrier, for example, to prevent flames or hot gases passing through, it's a bit like a propagation of fire, or preventing propagation of fire, if you like. And then the ability of a material to insulate, so it minimises temperature rise of the exposed surface of a building element. So, as it suggests, insulating one side of a building element to the other. And I guess the obvious thing would be in fire doors in buildings, for example. Some common examples. Emergency lifts, what I found out in the standard, emergency lifts have a rating of 120, 120, 120, so I mean 2 hours for each of those 3 elements. And I guess it's no surprising that's why cables with a WS52 rating are commonly used for lift mains cabling, for example, and main switchboard supplying emergency equipment, and I guess this relates to things like your fire pumps and emergency lighting and so on, also have the 2-hour fire limit. That's essentially the end of my presentation. I guess the one summary I thought I'd leave people with, and that is that the characteristics of fire and the way that cable materials behave in a fire are quite complex. But what I wanted to send or give people were the message that the standards that I've been talking about are well established. There's been a lot of research and development that went into putting these standards together, and so much so that testing of cables, the standards are very much repeatable and consistent, and so we are actually able to try to determine with a lot of scientific basis these characteristics of fire-rated cables that I've just been talking about. Thank you for your attendance. I'll hand it over to Ian, and if there's no questions now, he can progress with his presentation.
Thank you very much, Martin. There was one question that came up, which you may not have it in your chat window, Martin. It's a question from Jeff. For fire resistance of cables, understand that the circuit integrity is considered. For fire-resistant data and signal cables, is there any test standards which consider the ability of the cable to transmit data when exposed to fire conditions? Do you have a comment to that one, Martin?
Yeah, that's a very good question. Excellent question. The 331 series of standards and the equivalent 1660 standard does have a, I'm fairly certain it does have a test for data cables. So what I'm not sure about is, because what you're obviously alluding to is for data cables, you're looking for data integrity as opposed to a power cable, which is just looking for, you know, the ability of the cable to continue to carry current. So I would say, I mean, if you send me an email, what I can do is look into that particular aspect in a little bit more detail, because I'm reasonably certain that it is covered in the IEC standard. So if we can get, you know, email contact details out, I mean, I'm happy to receive an email about it and you know, discuss that issue outside of this forum, because I'm pretty sure that they do exist, but I'm just not clear on the exact detail of how the test is conducted.
Okay, there's another question there, Martin, from Gordon. What nominal voltage is applied to cable during tests such as mechanical rating?
That's a good question. Yeah, because you're not going to apply 240 volts during the mechanical rating, because there'd be some safety issues concerned with that. So normally the mechanical rating's done at a lower voltage. The impact test is done at voltages between 18 and 30. And similarly for the cut test, when I was researching this, I was asking myself the same question, and it's quite interesting. So they're done at much lower voltages for safety reasons, because there's a potential that the apparatus for testing the cable may become live.
Okay, if there's no further questions for Martin, I might start on the next part of the presentation. So does anyone else have a further question? Martin will still be there in the background, so if you can think of a question and you'd like to ask it at the end, please do so. Okay, so it's Ian Richardson here from ABB. Moving on from Martin's presentation, I'll be talking about essentially circuit breaker selection for the protection of cables. To keep things relatively simple, because we're looking at more or less the theory of what we need to do and why we need to do it. I'm not going to necessarily consider the elaborate cables rather that Martin has been just discussing, and I certainly didn't realise the level of testing that goes through for some of these fire-rated cables. I've mentioned the correct MCB selection, so obviously here we're talking about a miniature circuit breaker. I've done this purposely because it's a simplified way of looking at our circuit protection, and we're considering just the very basic range of cables. This can also be applied into much larger applications when we get into molded case or even ACBs. The style of protection that we're doing, the theory behind it, is pretty much the same. So it's a lot easier to look at a miniature breaker as the first point, and then that theory can be established for the rest of the range. So looking at what we're trying to do, most circuit protection, we're really looking at forms of overcurrent protection. That's divided into two areas, and you're probably aware of this. We have overload protection, which we're looking at a thermal overload. Essentially just the load is trying to pass too much current. And also we have short circuit protection, where we get into those areas of a much higher fault level, which we're trying usually through the protection to isolate that very, very quickly, and that prevents a degree of energy going through to both the load and the cables and the general infrastructure of the building or the network that we're involved with. So these are the two forms of protection, and our circuit protective devices, which I'll talk mainly a circuit breaker rather than a fuse. We're looking at both of these areas with the one device. Simple miniature circuit breakers, they cover both portions through their tripping curve. They cover both of these aspects. When we get into slightly more intelligent devices, such as multi-case breakers, they can have just a simple thermal magnetic trip, which is very similar in principle to a miniature breaker, but they can also have quite elaborate electronic trips, which gives us the ability to change the tripping curve in a number of ways. Why do we need to do it? Well, essentially, in a very simple view, you can see there's a small, pretty much a flexible cable here, which has been affected by heat. Obviously as cables carry more current, there'll be more heat generated, and depending on the cable, that can have an effect on the integrity of the cable, and we can get quite severe breakdowns if we don't do something about that. Even a small loading or a small increase in the thermal loading or the operating temperature of the cable can lead to a premature aging in the insulation, and we get breakdowns occurring of the cable itself. So it's actually quite important that we give good consideration to the selection of our protective device, in particular around about the thermal aspects of the protective device, so that we are offering the correct protection. As a basic rule, when we put a circuit breaker in a lot of power distribution situations, we're actually protecting the cable, which is leading to that load. We're not necessarily protecting the load, although that does come into it. From a thermal point of view, we would be rating the cable in accordance with the characteristics of the cable that we're trying to protect. Often it's looked at in the other way. We have a certain protective device, we choose the cable which is appropriate to that protective device. In AF 3000, which I'm sure you're all very, very familiar with, in one of the clauses, they give a couple of very simple formulas. With this, we've got an operating current, which is the IB value on the top line. Then you have the rated operating current of the overcurrent protective device, which is our circuit breaker, and that is then below the permissible current carrying capacity of the cable. So that's pretty simple. We know what current is being drawn by the load. We know the limit that the cable can actually withstand, and we have to choose a breaker which is going to protect somewhere in the middle. We've also got that second formula where the thermal tripping current of the overcurrent protective device, and this factor of 1.45. This number comes in quite importantly in a lot of the cable designs because it is an overload factor of the cable, which you'll see on one of the next slides. So moving to that next slide, there's another way of looking at this. We've got the operating conditions of the cable on the top line. So there is an operating current, which is a normal operating current or load that we're trying to protect. Above that will be the current carrying capacity of the cable, depending on which cable has been chosen. In the design of the cable manufacturers put this 1.45 value in there, which is our additional reserve value or an overload that the cable is actually designed to take. So it's 1.45 times the current carrying capacity of the cable. On the lower line, we're looking at our protective device. So the first element, which we've got, which is right here, we've got the rated current of our protective device, which is in the middle of our load current and the current carrying capacity of the cable. A couple of values here now of 1.05 and 1.2, depending on the characteristics of our breaker, and I've got some trip curves coming up. These values are quite important because that's the value where the breaker is likely to trip between those two in its thermal capacity. Then we also have this shaded area here, which is the additional reserve, again rated at 1.45 times this rated current. So the rated current being below the current carrying capacity, using our 1.45, we've got this extra reserve value here, but we should still be keeping below the ultimate limit of what the cable is going to be. So here's a couple of tripping curves of miniature circuit breakers. I would suggest most of you have probably seen the ones on the left-hand side. So most commonly people will tend to use a C-curve breaker, but there are also the Bs and the Ds according to the 60898 standard. A couple of other curves that you may have seen, which is a K curve and the Z curve, which are defined in the 60947 standard. So there are miniature breakers that can have any one of these 5 curves. Not all of the miniature circuit breaker manufacturers have them available. The most common ones are the B, C and D, but there's a couple of companies, ABB included, that have the Z curve and the K curve in addition. What we're looking at for this protection is the thermal part of the curve, which is down here. So on the B, C and D, it's a bit hard to read, but there's the breaker will commence to operate at around about 1.13 or 113% of its rated current up to 145%. So that's this 1.45 comes into play at that point here. On the K curve and the Z curves, which is, these are used a little more in Europe than they have been in other parts of the world as a consequence of the amount of manufacturers that do have that. These, in the thermal capacities, it's a little bit tighter, so it starts operating at 105% to 120%. So you can see the protection level is a little bit better on the Z curve and the K curve than it is on the good old B, C and D curves. The major differences between these devices gets down into this area where we're looking actually at the short circuit capacities and how quickly the breaker will operate under a short circuit condition. Typically, C curve is the general purpose. B curve can be used for long cable runs quite often. A D curve, a lot of people will use them in motor starting or high inrush applications. Z curve tends to be used more in electronic protection, so something where you want a real fast acting in the event of a short circuit. And the K curve is actually considered a better option to a D curve because it's not only a little bit tighter from a protection point of view in the thermal part, it's also a little bit narrower in its short circuit value, so it actually offers a higher degree of protection. There's a question come up from Alan, what's the use for K and the Z? Hopefully I just answered that. As I say, the Z curve commonly will be used for electronic protection because of the speed of operation, and the K curve, certainly in Europe, is more commonly used for either motor protection or transformer protection. So what happens with our cables passing current? As any cable or any conductor passes current, it generates heat naturally enough. There's a few formulas there about the amount of heat that might be generated. This will then affect the insulation which is surrounding the conductor, and it depends a lot on the cable design, which is Martin's area of expertise, as to what these characteristics could be. ways we can do further calculations, but this thermal resistance value is the way the heat is transferred through the insulation into the ambient area there. So these are considerations we have to be careful of, and the impact it can have onto what will become the life expectancy of our cable. The current carrying capacity of a cable or a conductor, it's a variety of factors will come into this. The conductor resistance, of course, depends on the type of material, the conductor cross-section. The thermal withstand depends upon the type of insulation material that surrounds the conductors. We also consider the ambient temperature, how the heat can be dissipated into the environment, which will then depend on how hot the cable actually runs. And then you've got your installation methods, and you'd be very familiar, of course, with the requirements in AS3008 and such, where if you bundle cables together, or if they're standing in free air or buried in conduit and so on and so forth, you've got varying current carrying capacities of these cables depending on the installation method which is employed. One thing which it certainly opened my eyes when I first saw this graph on the left-hand side is, let's say, a typical graph for a PVC V70 cable. Cables are generally rated for a 25-year lifespan. So running at its 70 degrees at its full current, the cable has a life expectancy of 25 years, as you can see from the green intersection there. Let's say we allow this cable to run at 90 degrees, so only increase the operating temperature by 20 degrees. According to the graph, your life expectancy will reduce to 2.5 years. Now, it's a little bit unrealistic to say that this is actually going to happen. You're not going to operate that cable at a temperature at 20 degrees above its rating continuously for that amount of time. But what the graph is actually highlighting is allowing a cable to operate at a higher temperature can have a very severe impact on the life that you would expect out of that cable. Your insulation will deteriorate, and it's mainly because you're using the cable outside of its designed capacity, its designed rating. So it's very, very important that we consider our circuit protection to allow the cables to perform at their best for their longest. With our ambient conditions, again, there's a variety of different ambient temperatures that can be encountered. It does affect the resistance of the cable. So again, you have to consider the environment where the cable is going in and how it's being mounted, as I mentioned before, and this is why it's covered very extensively in AS3008. So I think most of you will be installation contractors, you'd be well versed with that. So what are we trying to do with our miniature circuit breakers to protect the cable? Typical time current curve, as you can see here. That simple curve, the green curve for the miniature circuit breaker, as you can see, it's a little bit similar to the more elaborate curve that we saw earlier for the B, C and D and the K and the Z curves. That protection curve needs to fit under the time current characteristics of the cable, and that way we're offering proper and correct protection for our cable. So this type of curve is fairly similar to what you may have seen if you've done a discrimination study between an upstream breaker and a downstream breaker. And quite often, if you're doing a full study, you can actually incorporate the cable into your discrimination study to make sure that you've got the appropriate protection levels right throughout your network if you take your study to that degree. There are programs that are out on the marketplace that will do this for you as well. But it's quite important to get it there. Here we have a current carrying capacity or the capability before the cable starts to burn. And I can remember giving a similar presentation to this to a consultant in Perth, and it almost seemed like his favourite saying was, if you get it wrong, the cable burns. And it just rolled straight off his tongue. So he appreciated how important it was to get your circuit protection correct and protect these cables. Otherwise, the whole installation's under threat, and the cable potentially can virtually catch fire, depending on the characteristics of the cable, of course. So we want to make sure that our breaker protects the cable by tripping well before we get to this threatening value of the cable. And as I mentioned, this is not a reflection on the cable itself, because if we get to this value, we're asking the cable to do something which it's actually not designed to do. So we need to protect it correctly, choose the correct circuit protection to make sure that the cable is able to do its job. When we get to short circuit values, it's a very similar theory, except there's a slightly different formula here. Looking at our I²T type values here, we're actually looking at an energy value which is being pumped into that cable, which also will have a heating effect. Because with a short circuit, we're looking at an extremely high level of temperature which is trying to be thrown into that cable. It means that our breaker has to operate at a very, very fast time. So we don't want a slow operating breaker. In general terms, in our miniature breakers, yes, they do operate very, very quickly. As we get into the larger capacity breakers, they're not quite as quick, and there's some older technology breakers around which that certainly won't operate as quickly. I think if you're using good quality breakers, number one, and then selecting them according to the requirements of the short circuit value or the fault level of a particular installation, you'll get the breaking of those currents at the appropriate time. There is some values that the cable manufacturers will be looking at when we're talking about short circuit values, and if we have a very, very high current flow for a very short period of time, the cable is actually designed to withstand this, because they're designed to cope with a short circuit, provided that the short circuit is cleared in a reasonable time. So you will get a fast injection of heat into the cable, but because the circuit will be cleared by the protective device, the cable will be allowed to cool and you won't suffer any sustained damage. But the main message out of this is the most important thing is to make sure that you're selecting the appropriate protective device against the cable, or if you've already got a protective device, you choose the correct cable for that protective device. Depends which way you're approaching it. So that, in fact, is a fairly brief overview from my side on selecting the correct breaker. If there's any questions, by all means, please ask. If you've got a further question for Martin that you've thought of, please put that in as well. So we'll just give a couple of seconds. There's a couple of people typing I can see, so we'll wait for those to come through.
Ian, I'm back online, and while you were talking, I went and did a bit of research on Jeff's question about data cables, and in fact IEC 60331 does have a section that covers data cables, but unfortunately it's just still an integrity test in terms of checking that a current flows, a very small current, but it just checks that a current flows as opposed to, you know, the transmission of data. So it looks like that's one area that you know, some development could go on to look at data cables a bit better than what they're currently done.
Okay, I could see that. Thanks for that, Martin. I could see that there's a couple of people starting to type, but there's no questions have come through. So I'll ask again, has anyone got any questions that they'd like to ask either Martin or myself?
Well, people are thinking, Ian, when you were talking about the reduction in life, when you increase temperature, there's a rule of thumb that relates to that issue, and that is for every 10 degrees that you increase the operating temperature of, well, it applies to almost anything. Every 10 degrees you increase the temperature of operation, you decrease the life by 1/2.
I've actually heard that somewhere else, and I omitted to put it in the presentation, so thanks for that, Martin.
Yeah, that's okay. It's common for cables and you know, a lot of products.
I think it's fairly common from an installation breakdown point of view, so yeah, it would apply right across. Okay, we've been going slightly over an hour now, so thank everybody for their attendance. I don't think there's any other questions coming through. I would ask, if you don't mind, just to hang on for a couple more minutes. We'll be putting up their poll, and if you don't mind just having a look at these few questions in the webinar poll, and we certainly value your feedback. So, certainly from myself and from Martin, I'll speak on your behalf, Martin. Thank you to everybody for attending, and I hope to see you again on a future webinar. Thank you.